All right, welcome. We are going to wrap up section 3.4 by using our new tools to do some graphing. So let's take a look and see at our procedure. Take a look and see our procedure for graphing polynomials as it exists right now. So first, we're going to use that leading term test to determine the end behavior of the graph. We're going to use the leading term test to find the end behavior of the graph. All right, that's where we look at the positivity or negativity of the leading term, and then the coefficient, or excuse me, then the degree of that leading term. Okay, the degree of the polynomial. So then, after we find the end behavior of the graph, then we're going to find the zeros by solving f of x equals 0. And usually this is either by having it factored for us already, or by having something that we can factor, a function that we can factor. So then we will then find some zeros, find some values where we cross the x-axis. Those zeros are going to be the values that cross our x-axis. Then, once we find our x-intercepts, we're going to use those x-intercepts to generate intervals that we're going to look at in order to help us pick points to help us graph our function. Okay. Then we're going to use those intervals to select those additional function values. Then we're going to find f of 0, and this is going to give us the y-intercept. Then, if necessary, we're going to find additional points to help determine the shape of the graph. Okay? So let's take a look at a couple of these. We'll just do a couple examples, and then I'll turn you loose on your homework. But before we do, we need to figure out a way to incorporate these new skills into this procedure. Okay, all the black stuff is still the same. All right, so it still sticks 6 steps, but step 2 gets stretched out a bit. All right, again, option A, if we can, we always want to factor something if it's possible. It won't often work. All right, there just won't often be times when we'll be able to make it work. Option B is what's going to happen most frequently. All right, so we're going to use the rational roots theorem to find all the possible rational roots. And then we're going to use Descartes' rule of signs that we talked about yesterday to guide those guesses, to figure out, okay, what should we be picking? Then we're going to use synthetic division to find rational number zeros. We're going to use synthetic division to find rational number zeros. Once we have figured out, okay, we might want to start guessing these things with these 2 previous steps. Then, for each zero we find, we want to use that new function, step down that degree until we get to something factorable or a quadratic equation. Okay? Our goal is to get to something that we can factor or a quadratic equation. Then, the real number zeros are the coordinates of the x-intercepts, and we continue on. This is exactly the same setup that we had before. Okay? So I'm going to pause. I'm going to take a break for a second, allow you to pause and write all this stuff down. So go ahead and pause. If you want, feel free to rewind and listen to that explanation again. All right, so go ahead and pause in 3, 2, 1. So then let's take a look at a couple examples. All right, let's take a look at a couple of examples. All right, example 1. So step 1 of example 1 is going to be use the leading term test to determine the graph's end behavior. All right, so if we take a look at this leading term, we see that it is both positive and odd. By noting that it's positive and odd, we can say that our end behavior, as it goes to the left, our graph is going to go down, and as it goes to the right, it's going to go up. All right, feel free to refer back to that table and make that table whenever you're trying to graph some stuff. So that's step 1. Our end behavior is going to be down and up. Step 2. We want to find the zeros of the function by solving f of x equals 0. Let's try factoring this, okay? Whenever we have a cube, square, first degree constant type function, we want to see if factoring by grouping is going to help us. So if we take a look at these 2 terms, we want to ask ourselves, what do these 2 terms have in common? Well, they have an x squared in common. So let's factor that out. X squared times 3x minus 4. And then what do these 2 terms have in common? Well, not a whole lot, but this first term is negative, so we'll factor out a negative 1 and get 5x minus 2. Now, if we take a look at these 2 parentheses, it's not going to work out very well. Okay? So, option B, we're going to use the rational roots theorem to figure out what our possible rational roots could be. We want to find what those possible rational roots are going to be. So we take the last term 2 and all of its factors, so 2 and 1, divided by the coefficient of the first term, or the leading coefficient, and all of its factors, which are 3 and 1 as well. And don't forget, we always want to have positives and negatives on all these. Okay. So when we do that, we're going to be able to see that our possible leading coefficient, or our possible rational roots, are going to be plus or minus 2, plus or minus 1, plus or minus 2/3, and plus or minus 1/3. Okay, so those are all of our possible rational roots. Okay, so that is the first part of step 2. Okay, so we have all of those possible rational coefficients. Okay, so now we want to use Descartes' rule of signs to help guide our guesses and maybe eliminate some stuff for us. All right, so if we take a look at f of x, we can see that 3x to the cube, 3x to the third, minus 4x squared, we're going to have a sign change there. Then we do not have a sign change, and then we do have a sign change. So that is two total sign changes. Two sign changes, and then we have a third degree equation, so we're going to have a cube, or excuse me, 3 total solutions. So then we want to check and see what is f of negative x. Once we do that, we can say, all right, f of negative x is going to give us, that's going to be negative 3x cubed minus 4x squared plus 5x plus 2. We do not have a sign change from our first term to our second term. However, from negative 4x squared to 5x, we do have a sign change. And then from 5x to 2, we don't. So we have one possible negative one possible negative 0, and then no imaginary zeros. Apologies, my board is still, it doesn't get unjacked up just because you're not here, I promise. It's always, always, always not good. All right, so let's go away you. Cut, yep, bye. I'm going to draw a 0 up here, and then I'm going to drag it to somewhere that's useful for me. All right. So first I'm going to copy it. Then we could have 1 plus 2 is 3. 3 minus those 3 gives us 0 imaginary solutions. So that's one solution possibility. Or we could have 0 positive solutions, 1 negative solution, and 0 imaginary solutions. So those are our possible solution spaces. Either we're going to have 2 positives, 1 negative, and no imaginaries, or we're going to have 0 positives, 1 negative, and no imaginaries. So this might be a point where we want to use to check out these negative solutions. Let's start with these negative numbers, these negative solutions here. Because we know we have to have at most, or exactly, 1 negative solution. So once we find it, we can ignore the rest of the negatives. All right, so let's do that. Let's start with negative 1. Negative 1, we put it in the box. We use synthetic division to find rational number zeros. So negative 1, and then we grab our coefficients of our f of x function. So 3, negative 4, negative 5, and positive 2, which is just going to be looked at from now on as just 2. How's that sound? So once we do that, 3 comes down. Negative 1 times 3 is negative 3. 4 plus negative 3 is negative 7. Negative 1 times negative 7 is positive 7. Negative 5 plus 7 is 2. Negative 1 times 2 is negative 2. And hey, would you look at that? 2 plus negative 2 is 0. And we've found a 0. So x equals negative 1 is a solution, is a 0. So now we have a couple options. We have this function right here, which translates to 3x squared minus 7x plus 2. We can then use this function to find our remaining zeros, right? In order to do that, we have to do either factoring, completing the square, or the quadratic formula. All right. This thing actually factors, but you might not necessarily recognize that. So let's go ahead and use the quadratic formula, which is going to be negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. So if we take a look and we use this as our function, we have negative 7, which is positive 7, plus or minus the square root of 7 squared, negative 7 squared, excuse me, minus 4 times 3 times 2. And that is all going to be divided by 2 times a, which is 3. 2 times 3. Okay? So now let's simplify some stuff. So we have 7 plus or minus the square root of 49 minus 4 times 3 is 12 times 2 is 24 over 6. So we have 7 plus or minus the square root of 25 over 6, which is going to be 7 plus or minus 5 over 6, which then says, all right, we're going to have 7 plus 5 over 6, or 7 minus 5 over 6. 7 plus 5 over 6 is 12 over 6. And then 7 minus 5 is going to be 2 over 6. Well, these both reduce to 2 and 1/3. All right? So if we take a look at our solutions, we have found that x is equal to 2, x is equal to 1/3, and x is equal to -1. So x equals 1, 1/3, and 2. And if we take a look, there's 1/3. There's one of our solutions. There's 2. There's another one of our solutions. And then there's -1. And after we found our one negative solution, the other two were both real numbers, and they were both positive numbers. Okay? So that's how this works. So we have used our rational roots theorem and Descartes' rule of signs to help us guess a better number to start with. All right? So once we have this, let's go ahead and move on to step 2. So let's just list it one more time. So our real number solutions are x equals -1, 1/3, and 2. Okay? So step 3. We want to use those x-intercepts to generate the intervals for the function. Okay? So we start at -∞ to -1, -1 to 1/3, and then 1/3 to 2, and then 2 to positive infinity. Okay? So from there, we have generated our intervals. We have our intervals. So then we move on to step 4. All right? So we use those intervals to select some additional function values. All right? So what function value should we pick? Well, we should pick something from -∞ to 1, -1 to 1/3, 1/3 to 2, and then 2 to infinity. So let's pick some numbers, shall we? Well, -2 seems reasonable for our first interval. -2, okay, good, we got that. -1 to 1/3, I'm going to go with, let's go with